Okay, think about this for a second. What on Earth could possibly connect a star, a steam engine, and a living cell? I mean, they couldn't be more different, right? It sounds kind of crazy to think there's a single set of rules that governs all of them. But, well, there is.
And that rulebook, that universal guide to, well, everything, is called thermodynamics. Now here's what's so cool about it. It's totally empirical. Nobody just dreamed this stuff up from pure theory. Nope. It came from watching the world, seeing how things actually work. And the whole thing, the entire field, is built on just 4 laws. 4 simple, unbreakable rules. So, yeah, let's get into it.
All right, before we jump into the laws, we got to get the lingo down. It's super simple, I promise. First up, the idea of a system. A system is just whatever part of the universe you've decided to pay attention to. It could be a steam engine, a cup of coffee, or heck, even an entire galaxy. And everything else, everything that's not your system, we just call that the surroundings. Simple, right? But believe me, knowing what's in and what's out is absolutely crucial.
So here's the game plan. You can think of these 4 laws as the 4 main chapters in this rulebook. The first one, which we actually call the 0th law, yeah, I know, we'll get to that. It defines temperature. The first law, that's all about energy. Then there's the second law, and honestly, this one's the big one. It introduces a wild concept called entropy. And finally, the third law gives us a starting point, a 0 value for that entropy. The most important thing to remember, these aren't suggestions. They are absolute, universal laws. You can't cheat them, you can't ignore them, they just are.
Okay, let's start at the beginning with the ground rules, the 0th and 1st laws. These 2 lay the foundation by defining our most basic ideas, temperature and energy. And look, they might sound super obvious when you first hear them, but trust me, they are the bedrock that everything else in thermodynamics is built on.
You already know this from, well, just living, right? You pour a hot coffee, you put the mug on a cool countertop. What happens? Heat flows out of the coffee and into the counter. It keeps doing that until they're both the exact same temperature. And once that heat flow stops, we've got a special name for it: thermal equilibrium.
So, the 0th law just takes that idea and makes it official. And honestly, it sounds so simple it's almost funny. It just says, if object A is in equilibrium with object B, and B is also in equilibrium with object C, then A and C have to be in equilibrium with each other. I know, it sounds like a dumb moment, but don't let that fool you. That simple bit of logic is profound. It's the reason thermometers work. The thermometer is that middleman, object B, letting us compare the temperature of, say, our body and a cup of water without them ever touching.
And that's why the 0th law is so important. It gives us a real, solid definition of what temperature even is. It's not just a feeling, oh, that's hot, or brr, that's cold. No, it's the actual fundamental property that dictates which way heat will flow. Period. Without this law, our whole idea of temperature would just be, well, a bunch of guesswork.
Okay, so that naturally leads us right into the first law, which is all about energy. Specifically, we're talking about the internal energy of a system, which scientists label with a U. Just think of it as all the energy crammed inside your system, and you can change that total energy in only 2 ways. Either you add heat to it, that's Q, or you do some work on it, that's W. But here's the really important part. Internal energy is what we call a state function. All that means is that the system doesn't care how it got its energy. It doesn't remember if it was heated up or squeezed. All it knows is how much energy it has, right here, right now.
And this all boils down to one of the most famous and powerful statements in all of physics, summed up beautifully by Rudolf Clausius. The energy of the universe is conserved. That's it. You can't make energy from nothing, and you can't destroy it. You can only change its form, from chemical to thermal to kinetic, whatever. The total amount of energy in the universe, it's fixed. It never changes.
All right, now we're getting to the main event, the star of the show, the second law of thermodynamics. If the first law tells us we can't win, meaning you can't create energy for free, the second law is even more brutal. It tells us we can't even break even. This is the law that explains why things happen in one direction and not the other. It's the law that gives us the arrow of time.
So one way to put it comes from Lord Kelvin. He basically said, you can't build a perfect engine. It's impossible. You can't just suck up heat from, the ocean and turn all of that heat into useful work to power a boat. It just won't work. Some of that heat has to be dumped somewhere colder. There is always waste, always.
But that raises a huge question, right? If the first law says energy is conserved,
Why can't we be perfectly efficient? Why can't we just take heat and turn it completely into work? What is stopping us from building a 100% efficient machine? To answer that, we're going to need a whole new idea.
And that new idea, the answer to the puzzle, has a name: entropy. Now, entropy is seriously one of the most important concepts in all of science, but man, it's also one of the most misunderstood. The simplest way to think about it: entropy is just a measure of disorder, of randomness. That's it.
So, what the second law is really telling us is that in the real world, things only go one way. Processes are irreversible. You drop an egg, it shatters. It's never ever going to just spontaneously put itself back together. And why? Because breaking the egg increases the total entropy, the total disorder of the universe. The only time entropy doesn't increase is in some perfect imaginary process that's perfectly reversible, which, doesn't actually exist in reality.
So here's the bottom line, the big takeaway. For any closed-off system, and you can think of our whole universe as one big closed-off system, the total amount of entropy will always go up. Or at best, it'll stay the same, but it can never go down, and that is the arrow of time. It's why coffee gets cold, why we get older, why empires fall. It is the universe's constant, unstoppable march towards more and more disorder.
And that brings us to the final piece of the puzzle, the third law. So if the second law is all about the universe's slide into total chaos, the third law does the opposite. It defines what perfect, ultimate order would look like. It sets an absolute limit.
This one comes to us from the great Max Planck. He said that if you could take a perfect crystal, absolutely flawless, and cool it down toward absolute zero, its entropy would also approach zero. Think about that. At that point, all the atoms would be locked in a state of perfect order. No jiggling, no randomness, nothing. It's a state of ultimate tidiness, and that gives us a definitive floor, a true 0 point for entropy.
And this ultimate state of perfect order happens at a very specific temperature we call absolute zero. That's 0 Kelvin. For those of us who think in Celsius, that's minus 273.15 degrees. And let's be clear, this isn't just really, really cold. This is the coldest anything can possibly get. It's the fundamental limit of cold in our universe, the point where atoms basically stop moving.
But here's the kicker, the amazing little twist that comes with the third law. It's impossible to actually get to absolute zero. We can get mind-bogglingly close. Scientists have chilled things down to billionths of a degree above zero, but we can never hit the target. It's like the universe has this ultimate finish line of cold that we can run towards forever, but never, ever cross. Okay, so we've covered all four laws, the zeroth, first, second, and third. I know, it can all seem a little abstract, right? So let's bring it back down to Earth. Why does any of this actually matter?
The thing is, these four laws, they're not just abstract ideas. They are everything. They dictate the absolute maximum efficiency of every car engine, every power plant we will ever build. They're the reason chemists know which reactions will work and which won't. They are at the very heart of the processes of life itself. And yeah, on the grandest scale imaginable, they even hint at the ultimate fate of our entire universe.
And that leaves us with one last, massive, brain-melting question to think about. If the universe really is one giant, isolated system, and if the second law says its total entropy, its disorder, is always increasing, then what happens at the end? Where is all of this heading? What does that final state of maximum total disorder even look like? Yeah, something to chew on for sure.